Good morning, students. I am Professor B.Prakash, Associate Professor, HOD, Department of Physics, GBR Degree College, Bellary District. So this is a college comes under the management of V.V. Sangha, Bellary. So today I am going to talk about eyepiece, which comes under optical instruments, and this is one of the chapter in BSc 4-7, which comes under VSKU, Vijayanagara Sri Krishna Deva Raya University, Bellary. And under that syllabus, BSc 4-7, under the chapter name Optical Instruments, so this is eyepiece. So here, eyepiece, it is a combination of two lenses, field lens and the eye lens. Instead of using two lenses, if you use only one lens, there is a occurrence of chromatic aberration. Aberration will occur. In previous class, we discussed about aberration in the same optical instrument chapter in previous episode, I think. So there, due to the two aberrations, chromatic and spherical aberration, as we knew already, chromatic aberration is the aberration, it is due to the different colors with by R. So image is not clear. So image will have different colors. So this is aberration of chromatic, and another one is spherical aberration. So spherical aberration is not, it is one where we cannot get the final image at the one place. So it is not so clear. So therefore, if you use single lens in the eyepiece, so there is a chances of occurring spherical aberration and chromatic aberration. Therefore, combination of two lenses is which gives eyepiece. So they are called field lens and the eye lens. So it's, I mentioned here under Eisen's eyepiece. So there are two lenses are here. It is shown here. L1 is one lens, L2 is another lens. So here, field lens, it is a combination of two lenses. Eisen's eyepiece is defined as, it is a coaxial system of two lenses which are named as field lens and eye lens, and employed to obtain magnified image of an object. So an object is a coaxial system. On the single axis, the principal axis, these two lenses are fixed. So it is called coaxial system of two lenses. They are named as field lens and the eye lens, and these are employed for what purpose? It is employed to obtain magnified image of the object. Therefore, combination of two lenses, field lens and eye lens, combination of two lenses, it is called the eyepiece. So eyepiece having two lenses, field lens and the eye lens. So field lens is always towards the object in which we can able to view the object, and eye lens is towards the eye where we can view the image. So here field lens, so it is towards the, it is objective part, it's called the objective part. I mean eyepiece, so total it is the objective part near to the object. So this is the eyepiece near to eye. So eyepiece having two lenses, field lens and the eye lens. I defined just now, it is coaxially fixed two lenses, field lens and the eye lens, now to view the magnified image of the object. So here, after knowing what is meant by eyepiece, so you knew, so different optical instruments we are using for measuring different things in the lab, I mean in the laboratory. So eye is the natural eyepiece, natural magnified, I mean we can view the images everywhere we can go. Similarly, microscope is there, telescope is there, spectrometer is there. So these are the optical instruments where you can view the image for different purposes, different, wherever you go and you can find different things. So therefore, so microscope is one where you can view the magnified image for the minute particles. You can view in the form of if it is near, the object is near here. And for the longer distance, we can use the telescope in order to view the longer distant objects. So this is the eyepiece. Briefly I can able to explain, and different types of eyepieces. So there are 4 types of eyepieces are there. One is Huygens eyepiece, as I written on the board. Second one, the Ramsden's eyepiece. Third, Gaussian eyepiece. Fourth one, Kellner eyepiece. But according to our syllabus, VSQ Bellary syllabus, we have only 2 eyepieces. According to the syllabus, we have only 2 eyepieces. One is Huygens eyepiece. Second one is Ramsden's eyepiece. So let me explain. Single one, that is first one, it is called Huygens eyepiece. So it is written here. So this is the Huygens eyepiece. As I told you already, it is a combination of 2 lenses, field lens and the eye lens. So field lens is always towards the object, and eye lens is next to after that what we have after the field lens, we have another lens, it is near to the eye. So here these are the 2 lenses. So lens 1 and this is lens 2. And we have 2 plano-convex lenses. L1 is the plano-convex lens, L2 is the another plano-convex lens, and this is the convex surface. This is the convex surface facing towards the object. They are not facing each other, they are facing one another, and these 2 convex surfaces are facing towards the object. These 2 convex surfaces can able to catch the rays from the object. And here the ratio, they are in the ratio, F1 is in the ratio 3F and F2 is in the ratio F. So F and F2, they are in the ratio 1:3. So F2 focal length F, and F1 is 3F. Therefore, they are in the ratio 1:3. You can take in terms of 3:1. If you take with respect to field lens and the eye lens, it is with respect to eye lens and the field lens. So, and what is the distance between 2 lens? So this is 2F. So 2F, if F is the focal length of any lens, maybe field lens or the eye lens. So 2F is the distance between 2 lenses, F1 and F2. So this is the arrangement of. So these 2 lenses are arranged in a tube. So actually it is fixed in the tube. So this is the Huygens eyepiece. So here, what will happen in the Huygens eyepiece? According to this figure, we have briefly, I can able to explain what will happen inside the field lens and the eye lens. Totally inside Huygens eyepiece. So here, this is as we knew, this is L1 is the field lens, L2 is the eye lens. So this is the object and this is the eye. On one side it is the object, on another side it is the eye, in which can view the image, magnified image we can able to view. So here, this is the plano-convex lens, and as I told you, this is the convex surfaces are facing towards the object, and see here, these are the rays are coming from the distant object. See here, if you see the figure, they are incident at 2 parts, part 1 and part 2. After refraction, these 2 will meet here at A and B. So this is the position of the image. The image will form in between field lens and the eye lens. So here, from the distant object, it is passing through the field lens. After refraction, it will meet at A and B. From that, if you extend the rays, it will meet another on second lens. It is L2, and this is after refraction. So it will meet on the eye surface. So we can able to view them. But here, what will happen? So here, so this is a position of the image in which we have to keep the cross wires. We have to keep cross wires here in between field lens and the eye lens. If you keep the cross wires here, what will happen? So due to the lens, it is in between 2 cross wires. If you fix, then there is a refraction will take place of these cross wires, and the image is not so clear. Similarly, the rays, they will overlap on one another. So therefore, it is called negative eyepiece. Huygens eyepiece is called the negative eyepiece because cannot use cross wires. As I told you, if you use the cross wires in between field lengths and the eye lengths, thus there is a blur in the formation of image. The image is not so clear if you use cross wires in between two lenses, field lengths and the eye lengths. It is so blurred. So therefore it is called the negative eyepiece. Therefore, so due to this reason, negative reason, so this is not using for qualitative purpose. It is only used for quantitative purpose, not for qualitative. In order to measure the focal length or something else, we should not use. Only we can use this only for the qualitative measurement. For example, telescope, you can use the longer distance object, and microscope, minute particles you can be able to view, where we cannot use this for measure the perfect focal length of the different lenses. Therefore, this is called negative eyepiece. So here we have some equations regarding focal length and all. So for the achromatism, for the achromatism. So what do you mean by achromatism? Achromatism, it is a combination of two lenses. So here we have two lenses, field lens and the eye lens. So what is the purpose of using two combined lenses? In order to overcome aberrations, in order to remove aberrations. As you knew, there are two types of aberrations, chromatic aberration and spherical aberration. In order to overcome these two aberrations, we have to use achromatism. This is the phenomenon of combination of two lenses. We can overcome aberrations. It may be spherical, it may be chromatic. So here it is a combination of two lenses. As I told you, focal field lens and the eye lens. So we have some equations, d1 plus d2 divided by 2. So sum of two focal lengths, that is field length and the eye length, and divided by 2. We knew it is written on the board. So 3f plus f divided by 2 is equal to 4f divided by 2 is equal to 2f. So it is I already written here. 2f is the distance between field length and the eye length. Therefore, from this equation we came to know, so d is the distance between field length and eye length. This is by substituting all the values in the given formula, we got the value of d is equal to 2f. So this is 2f. Then for minimum operation, after doing this, next let me study to minimize. So minimize aberration. We have another equation, that is d is equal to f1 minus f2 is 3f minus f is equal to 2f. It is also proved this is we can minimize the aberration, that is particularly two aberrations as we knew. So it is the formula. So f1 minus f2, f1 is 3f, it is written here, minus f is equal to 2f. In another way also, we can d is the distance between two lenses will be 2f. By using 1 and 2, equation number 2 this is, so previous equation called as equation number 1. By using 1 and 2, I will write here f1 f2, equation number 2, and before this we had another equation, it is f1 f2 divided by 2. By cross multiplying, so what we will get? We will get 2f1 minus 2f2 is equal to f1 plus f2. So here, bring this f1 to this side. What we will get? 2f1 minus f1 and is equal to f2 plus 2f2 is equal to f1 minus f1, it is only f is equal to 3f2. So therefore it is also proved here, so it is 1 is to 3. So it is a relation between f1 and f2. So f1 is equal to thrice the value of second focal length. So this is focal length of first lens, this is a field lens. Field lens is the 3 times of eye lens compared to this is the ratio of eye lens and the field lens. So by using these two equations, we came to know d is equal to 1, and this is F1 is equal to 3F2. By using these two equations, we can able to minimize the chromatic or spherical aberration. And this is equation number 3. This is equation number 3. Just keep all these equations in your mind. And once again, we have to substitute all these values for the equations. It is 3 in 1. Next. 3 in 1. So D is equal to 3F2 plus F2 divided by 2 is equal to 4F2 divided by 2 is equal to 2F2. Equation number 4. So next we have to find out the expression for equivalent focal length. Equivalent focal length means with combination of two lenses we have one equation as we knew for the equivalent focal length 1 by f equal to 1 by f1 plus 1 by f2 it is minus d divided by f1 into f2. So substituting all these values. Let me substitute all these values. This is 3f2, this is f2 minus d 2f2. We got all these values in the previous equation. This is 3f2 and f2. So here f2 get cancelled. 3f2 is the LCM. By substituting all these values, we got 1 by f equal to 1 plus 3 minus 2 divided by 3f2 is equal to, so 3 plus 1 4, 4 minus 2 is 2 by 3. 2 by 3 f2 divided by f2. So what is capital F? We have to reverse the value. It is 3 by 2 f2. So this is the combination of two lenses. So we have different equations 1, 2, 3, 4, and from these equations we came to know these are the equations who can minimize the chromatic or spherical aberration, and for the achromatism, and this is the condition to separate two lenses. So this is another figure. So it is a continuation of eyepiece. Just now I explained what I mean by Huygens eyepiece, and we knew different reasons. What is D, F1, F2, and what is the difference between two lenses. So you knew. I mean, in previous equations we already studied what we mean by how to minimize the aberration and all. And this is the second figure. So this is a question of cardinal points in Huygens eyepiece. So cardinal points. This is in previous class and previous part. I already explained what we mean by cardinal points. It is the combination of two focal points, two principal points, and two nodal points. So these are 6 points. They are called cardinal points. So here, if you see the board, so if you see the figure, so we can able to explain. So these are the different positions on here. So here, first L1 is the field length, and L2 is the eye length, and this is the convex surface. It is always towards the object, and this is the eye, towards eye. And here I am written here. So here, so N2. So this is N1 and this is N2. So N1 and N2 are the two nodal points. So I told you two pairs of two nodal points, two focal points, two principal points. They are called the cardinal points. If you see the figure, we have all the 6 points here. So here, first one, so F1 is the focal point. I mean, this is the plane and this is the plane. F1 is the focal point, first focal point. So this is the second focal point. And this is the plane passing through S2, P2, N2. So here P2 is the second principal point, P1 is the first principal point. And this is N2 and N1. These are the two nodal points. And here F1 and F2, these are the two focal points on the principal axis. So axis is common for all the parts and points. So here, so if you see the figure, so here first one, So what is the distance between two lengths? We have to derive this equation 2f2. We derived this equation 2f2 and this is 3:1. The ratio between the ratio of two focal lengths of field lengths and eye lengths should be 3:1. So this is 3f and this is 3f. In the previous figure I have already told about all these things. And this is 2f2. 2f2 is the distance between field lengths and the eye lengths. So this is 2f2. And here, so if you go on study one by one, so this is f1. f1 is the first focal point. It is, so this is the first focal point. It is away. It is right side from the field length. It is the right side from the field length. And this is f2. So this is right side from the eye length. There is a new here. And so this is 2f2 and this is 3f2. 3f2 we derived in the previous class. From that equation, what is the distance between the field length and the first principal point? So P1 is the first principal point. So it is at the distance 3f2. 3f2 is the distance between first field length and the first principal point. So here it is mentioned here. And this is f2. What is f2? So f2 is the second focal point. So f2 here it is the focal length f2. It is here in between this eye length. It is left to the eye length. Some of the points are right to the eye length. Some of the points are left to the eye length. So here P2. So P2 is the second principal point appeared left to the eye length. So first principal point is appeared right to the field length. It is very important. Right to the field length at the distance of 3f2. And the second principal point, it is appeared left to the eye length. It is P2. The distance between this is f2 and this is 3f2 and this is 2f2. And here another two points are here. It is n2, f2. What is the distance between n2 and f2? So here n2 and f2. So what is n2 and f2? It is the distance between second nodal point and the second principal point. It is the distance should be 3f2, f2. And this is another one, n1 and f1. So it is the distance between first nodal point and the first focal point. So this is equal to 3 by 2 f. So in this way, you can find the distance between, so f2 is there, 2f2, 3f2, 3f2, f2, 3 by 2 f2. So here, if you are looking at this figure, you came to know these are the positions of the 6 points. They are combined, they are called as cardinal points. So, 2 nodal points, 2 principal points, 2 focal points. So, it is mentioned here on the board F1, F2, they are the 2 focal points, P1 and P2, it is 2 principal points. So here, important to note here, N1 and P1, it is meet at only 1 point, and N2, P2 is meet at only 1 point. And F1 and F2, they are separate. So, P2 appears right of the field length, and so this one. So P2 appears left of the field length. So this is a combination of 6 points in the Huygens eyepiece. It's also very important in the view of the examination. So therefore, dear students, and this is very important class I think. So it comes under eyepiece. So in this part, I explained what you mean by eyepiece. It is a combination of field lengths and eye lengths, and where it is appeared before and after. And there are 4 types of Huygens eyepiece. Pieces are there, and I told you and I explained. I mean, in the form of equations, how to minimize chromatic aberration and spherical aberration, and how to minimize achromatism. It is a combination of 2 lenses, and we came to know different equations. And so this is the last figure, the cardinal points in the Huygens eyepiece. So as I told you just now, I explained. And dear students, follow all these things and prepare for the forthcoming examinations. So all the best. Thank you for hearing.